SwayamPrabha. Digital India. Educated India.
Hello everybody, welcome to the first lecture, and in this lecture we are going to discuss about the mathematical concepts that will be required in the coming lectures. Okay. So, the main topic starts from lecture 2, and this lecture we are going to work with vectors and tensors a lot, and I will tell you what tensors are. Okay. So, this is working with vectors and tensors. All right. So, start with vectors. So, we all have learnt about vectors in our schools. We say that a vector is something which has magnitude and direction, right. So, it could be something like an arrow with a pointer. So, the length of the arrow is the magnitude and the direction is the arrow itself, is not it? All right, that is the basic concept, but more important, a vector is independent of the coordinate system. So, you look at a vector from one coordinate system or from other coordinate system or from some other coordinate system, the vector does not change. So, it is independent of the coordinate system. Think for example, of a coordinate system whose bases are E1, E2, E3, the Cartesian coordinate system. Okay. They are perpendicular to each other. So, it is a Cartesian coordinate system, and suppose this vector that we have here, we say it is V, all right, the vector V, and it is in the E1, E2 plane making an angle of 45 degree from the E1 axis, all right. So, this angle is 45 degree. So, what are the various components of this vector in this coordinate system? If I say V1, the component along E1, then this is the vector V dot with E1, right. Similarly, you can get the second component and third component, and as this vector is lying in the E1, E2 plane. So, the three components are 1 by root 2, 1 by root 2 and 0, is not it, assuming that the vector is of unit magnitude. So, the components of this vector with respect to this coordinate system is 1 by root 2, 1 by root 2, 0. You take another coordinate system, then the component of the vector with respect to other coordinate system will be something else. Okay. So, it is the component of the vector which changes from one coordinate system to the other, but the vector itself does not change. Okay. Please remember that we have this vector, and I put this big bracket to denote that I am writing the components of this vector as those three entries in a column. So, this becomes 1 by root 2, 1 by root 2 and 0, okay, and this is in E1, E2, E3 coordinate system. This column that you see here, it is the representation of the vector in E1, E2, E3 coordinate system. If you choose another coordinate system, let us say a red coordinate system, where one of the axis is along the vector itself. Okay. So, we have E1 hat, E2 hat, and E3 hat is along E3 itself. So, in the new coordinate system, what will be the components? The component along E1 hat, since E1 hat is along the vector itself, it is 1, the other two components will be 0 then, right. So, in the new coordinate system, the representation of that same vector in the new coordinate system, E1 hat, E2 hat, E3 hat. So, that is going to be 1 0 0, right. Okay. So, I hope you got some idea that the vector is independent of coordinate system, but its representation or its column form changes from one coordinate system to the other coordinate system. All right. So, I will just write there. Okay. So, you could also write it as the vector V is equal to summation over I equal to 1 to 3 V I E I, okay, the three components summed here, or you could write it as summation over I equal to 1 to 3 V I hat E I hat. So, you see when you sum it, you get the same vector, but individually the components are different, all right. And in this course we will denote vectors by putting a tilde below it. Usually we denote vectors by putting a arrow above the vector, right, like you see here. We have put an arrow above the vector, but in this course we will put a tilde below it to say that it is a vector. Okay. So, V we will write it as V with a tilde below, and I will tell you why we use this tilde. Okay. All right. Now, what can you do with vectors? So, there are several operations that you can do with vectors. Operations with vectors. The first one is the usual dot product, which all of us know. So, we have two vectors A and B, you see vector with a tilde, right, A dot B. So, what is it? You simply take the individual components, multiply them and sum it, right. So, this is then summation over A I B I and I equal to 1 to 3, correct. You could also write it in some matrix form. You could write this as a row of A multiplied with the column of B. So, you have A1, A2, A3, B1, B2, B3, right. And this first one is 1 cross 3 and this is 3 cross 1. When you multiply it, you get 1 cross 1, right, a scalar quantity. So, dot product of vectors gives you a scalar quantity. But there is another thing that you can see now. The first one, because it is a row which is the transpose of a column, right. So, we could also write it as the vector A transpose multiplied with B. So, A dot B we could also write as the vector A transpose multiplied with B. Okay. Then you have cross product. A cross B, and I guess all of you know what it gives you. So, this is basically A 2 B 3 minus A 3 B 1. So, this is the E 1 component plus A 1 B 3 minus A 3 B 1, that is the E 2 component, plus A 1 B 2 minus A 2 B 1, and that is the E 3 component. Okay, the 3 components of this cross product. Okay, now, we can also write the same thing in a column form. Okay. So, we have column of A cross product with column of B, and then the right hand side we have the 3 components written in this column, A 2 B 3 minus A 3 B 2, A 1 B 3 minus A 3 B 1, A 1 B 2 minus A 2 B 1. Okay. The 3 components written in this column, this is something that you have seen, but you know we can also write it as a matrix times the vector B. So, we have this column of B, B 1, B 2, B 3, and a matrix. It is a very special matrix which has 0 on the diagonal, and the off diagonal components are negative of each other. So, this is basically a skew symmetric matrix. The components of the matrix are formed by the components of A. Okay. For example, this first row second column 1 2 first row second column is formed by the third component of A. So, we have A 3 here. First row third column is formed by second component of A. So, whatever is missing you take that component, first row third column second is missing. So, it is formed by second component A 2. Second row third column 1 is missing. So, it is formed by first component of A 1. And then the tricky thing is this first one A 3 has to be with a minus sign, A 2 remains A 2 and A 1 becomes minus A 1, and then you form this skew symmetric matrix. Okay. So, this is A 3, here we have minus A 2 and here we have A 1. All right. So, there is a nice way to form this matrix, and when you work out this matrix times the column, you will indeed see what you have on the left hand side, okay, the cross product. And this matrix, so people say that the column of A is actually the axial, you know, this name axial of this skew symmetric matrix. So, whenever you have skew symmetric matrix, you can form a column from the 3 entries in that skew symmetric matrix, or whenever you have a column you can form a skew symmetric matrix in the way I just told you. All right. So, this is a different way to visualize cross product. Okay. And what you have to remember also, that just like the vector which is independent of the coordinate system, these operations dot product or cross product are also independent of the coordinate system. For example, A dot B is summation of A I B I. If you use different coordinate system, then it would be summation of A I hat B I hat, but the product with the summation has to be the same. So, dot product will not change. Likewise, for the cross product also. So, they are geometric, they have geometric meaning. What is dot product? You have two vectors, then the dot product is take the magnitude of each of the vectors, multiply with the cos of the angle between the two vectors. So, it comes from geometry. You change the coordinate system, magnitude of the vectors do not change, the angle between the vectors do not change. So, the dot product will also not change, right. So, dot product and cross product are basically coordinate free operations. When you write it in terms of the components of the vector which change, but as a whole it has to be the same. There is another interesting operations that one can do with vectors. You see, dot product gave you a scalar, cross product gives you vector. There is another operation which is called tensor product A, tensor product B. So, the tensor product is denoted by this cross symbol with a circle, all right. So, this gives you what is called a second order tensor. Okay. So, this is the first time we are learning about tensor. So, this gives you a second order tensor. So, it is second order. So, we put two tildes below, okay. Second order tensor. The way to see this easily is we say whenever we have tensor product and you try to write it in the column form, then you take the first vector as a column, but the second vector as a row, exactly reverse of what we did with the dot product. In dot product the first one was the row, right, but here the second one is row. So, since the second one is a row, so therefore, it becomes the transpose, is not it? It is the transpose of the column. First one is 3 cross 1, 3 rows, 1 column. The second one is now 1 cross 3. So, when you do the multiplication, what you get is actually a matrix, is not it? It is a matrix, and the individual components are denoted using two subscripts C I J. Okay. So, C I J, for example, the ith row and jth column. What is C I J? When you work this out, it is simply A I into B J. So, you see, for the vectors the components have single index subscript, whereas for C you have two subscripts, therefore, it is called second order tensor. Okay. And so, we use two tildes, one tilde for a vector, two tildes for second order tensor, three tildes for third order tensor, all right. You know, we can also see it that the C was A tensor product B, right. Now, why do not I expand A as summation over I, A I, E I, okay, the vector A, and this has to be tensor product with the vector B. So, that summation over j B j E j, correct. Now, we could write the same thing as double summation I j A I B j E I tensor product E j. Now, contrast this with the vector representation. For a vector, we say A is equal to summation over I A I E I. So, we have I going from 1 to 3, because it has 3 basis vectors E 1, E 2, E 3. For second order tensors, the basis vectors are these quantities E I tensor product E j, not just E 1, E 2, E 3 with a tensor product. So, how many of the basis vectors are there? There are 9 of them for I equal to 1 to 3, j equal to 1 to 3. So, there are 9 basis vectors. Okay. So, basis tensors. So, there are 9 basis tensors. So, any tensor you could write it in terms of these 9 basis tensors. If you change the coordinate system from E 1, E 2, E 3 to E 1 hat, E 2 hat, E 3 hat, then your basis tensors are E I hat tensor product E j hat. Okay. And the component with respect to that basis is C I j, all right. So, here this A I into B j is C I j, and for a general second order tensor. So, we write that C is equal to summation over I j C I j E I tensor product E j, and C I j is then the component of the tensor C with respect to the basis tensor E I tensor product E j. Okay. Let us see what we get it in the matrix form. So, this double summation, take one of the terms from there, let us say C 1 2 E 1 tensor product E 2. Now, if I write it in the column form, the first one will be a column, where the second one becomes a row. Now, the column form of E 1 in the E 1, E 2, E 3 coordinate system, what will that be? That simply 1 0 0, right, because component of E 1 along E 1 is 1, along other directions it is 0. So, E 1 becomes 1 0 0, whereas E 2 becomes 0 1 0. Remember, these are the representations of E 1 and E 2 in E 1, E 2, E 3 coordinate system itself. If you use some other coordinate system to represent E 1, you will get something else. You will not get 1 0 0. You have to first find the components in the new coordinate system and then write those components in the column. Okay. Anyway, so in this coordinate system, now you work out this multiplication, and what do you get? You get a matrix 3 by 3, where only the first row second column is non-zero, and that is C 1 2, rest all are 0. All right. So, similarly, you have several other terms in this representation of tensor, and now you can see where is C I j going. So, second order tensor, when you represent it in a coordinate system, you get a matrix. Okay. For vectors you get a column, but for tensors you get a matrix, and the coefficient with respect to the basis vectors, they form the components of the matrix. Okay. And C I j goes in the ith row and jth column, right, you can see it here. So, I will just write here all right, and the C with this big bracket. So, this is the matrix form of the tensor C. And the matrix form will change from one coordinate system to the other coordinate system, but the tensor itself will not change. Okay. So, you could write this same tensor C as double summation I j C I j E I tensor product E j, or as double summation I j C I j hat of E I hat tensor product E j hat. So, two different ways to write the same tensor, because we have used two different coordinate system. So, from here the matrix form has C I j, right, whereas from here the matrix form has got C I j hat. So, we get two different matrices, but the tensor itself is the same. Okay. And just to give a recap, the vector with a single tilde, then we say it is a first order tensor, okay, whereas scalars without any tilde it is a scalar, and then we say it is a 0th order tensor. You put 2 tilde, it is a second order tensor, you put 3 tilde, it becomes a third order tensor, okay, and you can keep on thinking of higher order tensors also. All right. The next thing is, how does a second order tensor multiplies with a vector? Okay. All right. So, suppose we say A is equal to C times B. Okay. So, C is the second order tensor, B is a vector, I want to multiply them and I want to see what do I get. So, I am going to write the full form of C and B and let us see how do they multiply. So, the first one C has got double summation over I j C I j E I tensor product E j. The second one has got a single summation say over k of B k E k. And now we have to define this multiplication. So, we will say that the second order tensor and the first order tensor, when they multiply, then we take the second vector from the tensor. So, E j and E k and take their dot product. So, that is how we define the multiplication. You do not take E I and E k, you have to take E j and E k. Take the dot product and let us see what we get. So, two vectors you take dot product, it becomes a scalar, right. So, here then we have triple summation, right, we have 3 I j k C I j B k. So, all the scalar quantities you first write them together, and then we have the vector quantities. So, we have E I tensor product E j into E k, and we know we have to take the dot product of E j and E k. So, this becomes C I j B k E I of E j dot E k, because that is the definition of multiplication. So, what do you get when you dot E j and E k? E1 dot E1, what is it? 1. E1 dot E2, it is 0, right, because they are perpendicular. So, when j and k are same, it is 1, otherwise it is 0. So, there is a very nice function in mathematics which is called Kronecker delta function, and we write it as delta I j, delta subscript I j, and we say it is equal to 1 if I equal to j, and it is equal to 0 if I not equal to j. Okay. So, we can use this Kronecker delta here, and it becomes triple summation C I j B k E I delta j k. And now, you have to see, as per the definition, if j and k are not the same, you get 0. So, think of a summation over k. So, you have k equal to 1 to 3. So, that summation will give you a non-zero quantity only when k is equal to j, right. So, basically we can actually get rid of the summation over k, and wherever we have k, we replace it with j. Okay. So, this then becomes summation over I j C I j B j, see k has been replaced with j, times E I, and that is your vector A, right. To begin with, we said A is equal to C times B, correct. And you see carefully, if you put your bracket here, is not this A I, because vector A you could write it as A I E I. So, this is basically A I. So, what we see is that when we multiply a second order tensor with a vector, we get a vector, and the components of the vector are given by this formula. So, A I is equal to summation over j C I j B j, right. If you try to write this in a column form, then this is basically the ith row of C matrix multiplied with the column of B, see B1, B2, B3, Ci1, Ci2, Ci3. You multiply it, you get what you have here. So, this actually implies, if you want to get the whole column of A, A1, A2, A3, then it is simply the matrix C times the column of B. So, what we have found out finally is that if you want to multiply a second order tensor with a vector, the resulting is a vector, and to get the column of the resulting vector, you simply multiply the C matrix with the column of B, usual matrix vector multiplication. So, I will just write here, with this in hand, we can actually go back to our cross product definition. Do you recall when we had A cross B, then we said in the column form A cross B was actually the matrix times the column of B, is not it? So, now in the tensor form we can say that the resulting vector C, which is A cross B, could also be written as second order tensor A times B, because second order tensor times vector is equivalent to matrix vector multiplication. And now this second order tensor A, its column is this skew symmetric matrix A, okay. And we say that this is skew symmetric tensor. Okay, I hope all of you are with me. So, we have to always differentiate between tensor and its representation. Representation is the matrix which changes from one coordinate system to the other, whereas tensor is independent of the coordinate system. The other thing is, for a vector we know that V I is equal to V dot E I, is not it? For a tensor, if I let us say I want to extract the coefficient of the tensor, what should I do? So, CKL for example, what is its formula? Okay. So, we are going to work that out. So, I will prove you that CKL is equal actually C times EL dot with EK. Can you see how could you get that formula? Suppose I want C12, okay. Let us see for C12. So, C12 means C times E2 dot with E1. So, this is right now a tensor representation. Let us think of writing this in the matrix form. Okay. So, C becomes the C matrix, E2 becomes the column of E2 and E1 becomes the column of E1. So, this is same as C matrix, the whole C matrix C11, C12, C13, the whole C matrix multiplied by E2, and E2 is then 0, 1, 0, right. You multiply these two, you get a vector or a column, and then I dot it with E1, which is 1, 0, 0. So, can you see what you will get? Within that small bracket you have matrix times this vector 0, 1, 0. When you multiply, you simply get the second column of C matrix. Okay, so, you get C12, C22, C32, the second column, and then dot with 1, 0, 0, and you get C12, right. If you want to extract C12, it is C times E2 dot with E1. Okay. That is the way you can extract the component of a tensor relative to its basis tensor. All right. Similarly, you can also show when you multiply two tensors, multiplying two second order tensors. So, there are actually various forms of multiplication. One is where you multiply two second order tensors and you get the second order tensor itself, a different second order tensor. Okay. So, suppose we have C equal to A into B. So, now we have to see how does this multiplication work out. Okay. So, we can expand the whole thing, I mean the right hand side, and let us see what we get. So, A is then summation over I j A I j E I tensor product E j times B, which is again double summation over let us say K L of B K L E K tensor product E L, right. So, now let us bring all the scalar things together and the vectors on the other side. So, we have 4 summations I j k L A I j B k L, right, E I tensor product E j multiplied with E k tensor product E L. So, this multiplication has to be done such that the inner vectors that you have, you take the dot product of the inner vectors. Okay. Dot product of the inner vectors, which are E j and E k here. And let us see what we get. So, you simply have delta j k, right. So, you have E I tensor product E L. See, j and k are gone and only E I and E L are present into delta j k. Now, how to work this further ahead? So, we have two summations, 1 over j and 1 over k, and then we have delta j k. So, you know what to do, right. Delta j k is equal to 1 only when j is equal to k. So, there are two ways to proceed. Either you remove the summation over j and replace j with k everywhere, or you remove the summation over k and replace k with j, right, just like we were doing earlier, but now we have two ways to go ahead, because we have summation over both j and k. So, let us suppose we remove summation over j and replace j with k. So, we have triple summation I k L A I k, because j gets replaced with k, B k L E I tensor product E L, correct. And we can write the same thing as summation over I L and then a summation over k of A I k B k L E I tensor product E L. Okay. And you see this has to be C, the tensor C. So, do not you think the thing inside the bracket is actually C I L, is not it? So, this thing inside the bracket is nothing but CIL. So, now we know what happens when two tensors multiply, what happens to its matrix form. So, CIL is simply summation over k of AIK into BKL. And can you see what this is really? This is actually we take the ith row of A, AI1, AI2, AI3. So, that is the ith row of A matrix multiplied with lth column of B, is not it? To get CIL, you take the ith row of A, multiply with lth column of B. So, to get the full matrix C, you then simply have to do A matrix into B matrix. So, this implies that your C matrix is simply A matrix times the B matrix, a very simple formula finally. So, this means when two tensors are multiplying, then the multiplication that we worked out is as if you just multiply the matrix form of the two tensors in the usual way, and then the product matrix that you get is the matrix form of the resulting tensor. Okay? Very simple. So, this is about tensors. No, there will be many more things as we proceed in the lecture, some new things we may have to learn. So, that I will address you as we work out the lecture. Okay? There is also something called rotation tensor. So, this is the physical rotation. You have a vector, you rotate, you get a new vector. So, we are thinking it physically, but mathematically what should you do on that vector to get the new rotated vector? So, this rotation is actually done through the rotation tensor. Okay. So, you can think of a set of 3 perpendicular vectors E1, E2, E3, and then it gets rotated into E1 hat, E2 hat and E3 hat. Okay. For this rotation, there is always a unique rotation tensor. So, you have a set of triad 3 vectors and another set of 3 vectors. You can always find a rotation so that it maps you into the new set of 3 vectors. Okay. From the first set of 3 vectors, you multiply and you get the second set of 3 vectors. So, there is a unique rotation to do this operation. So, we will say that E I hat is equal to R times E I for each of the I equal to 1 to 3. All right. And this rotation has got a unique property, this rotation tensor. It turns out its matrix form is orthogonal matrix. Okay. So, R we say it is a orthogonal tensor, and its matrix form is a orthogonal matrix, and such matrices have unique property, that is, you take R, multiply with its transpose, or you take R transpose and multiply with R, then you get identity, an identity matrix. What does this mean? So, if we look at the matrix form, then we have R matrix multiplied with the transpose of the matrix, giving you identity, right, 1 1 1 0 0 0 0 0 0. Suppose I call this matrix C, then what is C I j? So, C I j is nothing but delta I j, right. It is equal to 1 when I is equal to j, that means the diagonal is 1, off diagonal is 0. But you also know from the matrix multiplication you have R into R transpose. So, we just worked out C I j when you have two matrices multiplying, the resulting matrix coefficient C I L, for example, is A I k B k L, right. So, what will be C I j? So, it will be a summation over some k R I k into R transpose k j, is not it? The inner index is summed. You see the inner index is summed. But then R transpose k j is same as R j k, is not it? What do we do in transpose? We just flip the off diagonal components, right. So, this is same as summation over k R I k R j k, which is equal to delta I j. So, can you see its meaning? So, this says you take the ith row of R and jth row of R and you take the dot product, right, dot of ith row and jth row, that is equal to delta I j. So, if you take two different rows of this R matrix and you dot it, you get 0. If you take a row and dot it with itself, you get 1. So, this tells us that the rows of this R matrix are perpendicular to each other. Similarly, you can also prove that the columns of the R matrix are also perpendicular to each other. So, this rotation matrix is very unique, that the rows and columns of this matrix so I will say two rows, any two rows, and same thing goes for columns of this matrix are, we say, orthonormal to each other. So, basically if the two rows are different, it is 0, if the two rows are same, it is 1. So, that means orthonormal, ortho for perpendicular, normal for 1 normalized. Okay. So, that is about the rotation tensor. Let us see an example of how will the rotation matrix look like. So, we have this E1, E2, E3 coordinate system. And suppose I rotate this coordinate system and think of a new coordinate system E1 hat, E2 hat and E3 hat, where E3 hat is same as E3, but E1 hat and E1 are rotated by theta. Okay. So, how will the rotation matrix look like? That is the question here. What is this R equal to? The components of R. Now, do you recall for a tensor what is R I j? You can go back. You see C k L is C times E L dot E k. So, R I j is then rotation tensor R into E j dot with E I, but by definition of this rotation tensor R into E j is nothing but E j hat dot with E I, correct. So, do you see now what is R I j? So, the jth column of this rotation matrix is the E j hat vector written in the E1, E2, E3 coordinate system. Can you see it? So, I have this rotation matrix, let us say j is equal to 2. So, we have R 1 2, R 2 2, R 3 2. So, R I 2 is simply E 2 hat dot E I. So, R 1 2 for example, is E 2 hat dot E 1, the component of E 2 hat along E 1. R 2 2 is E 2 hat dot E 2, the component of E 2 hat along E 2, likewise for R 3 2. So, this column is basically E 2 hat itself, but written in E 1, E 2, E 3 coordinate system. That is the column E 2 hat written in E 1, E 2, E 3 coordinate system. So, for this example, can you guess what is E 2 hat? From the picture that you see, can you guess it? So, this angle is also theta. So, when you say E 2 hat dot E 2, you get cos theta. When you say E 2 hat dot E 1, you get minus sin theta, right. It goes in the backward direction. So, what is then R 1 2 E 2 hat dot E 1, that is minus sin theta, R 2 2 that is E 2 hat dot E 2, that is cos theta, and R 3 2 E 2 hat dot E 3, that is 0, right. Similarly, you can think of the first column of R matrix. The first column of R matrix is the column form of E 1 hat in the E 1, E 2, E 3 coordinate system, and the third column of R matrix is the column form of E 3 hat in the E 1, E 2, E 3 coordinate system. So, when you work everything out, you will finally see that the rotation matrix is simply cos theta minus sin theta 0, sin theta cos theta 0 0 0 1. Well, let us see, the third column is simply 0 0 1 because E 3 hat is same as E 3. Okay. So, that is about vectors, tensors, rotation, and in the next lecture, which is actually going to be the first as far as the topic is concerned, we will start with the traction vector. Okay. Thank you.